So there's multiple ways we can express concentration, so how much solute there is per solvent. The two that we're going to deal with, though, are going to be molarity and mole fraction. Molarity we should be familiar with, mole fraction is going to be new, but it's not much different. So molarity is moles of solute divided by liters of solution. And liters of solution, notice how it's not liters of solvent, it's the total volume created after you mix those two. Molarity can change with temperature too, because when temperature changes, you're going to change the density of the solution, and so it's going to make the volume go up or down. So if you mix together a solution at 25 degrees and then the room warms up to 50 degrees, it's going to change the molarity of that solution. Mole fraction, however, though, is just the ratio of moles of A divided by the moles of A plus B plus C all the way to Z, however many different things there are. And so if you have salt and water, it'd be the moles of salt divided by the moles of water plus the moles of salt. Mole fractions are nice because they do not change with temperature. If you change the temperature, there's nothing about volume in here, so the mole fraction would be identical. So a quick example of molarity, 3.75 grams of sodium chloride salt is dissolved in water. The total volume of the solution after we mix those two is 768 milliliters. What is the molarity of the solution? So remember that molarity is moles divided by liters of solution, and in this case we've got grams of our solute and we've got milliliters, so we are going to need to convert both of those. And so finding the moles of sodium chloride, that's a pretty easy calculation, and then just converting 768 milliliters over to liters by moving the decimal place, and then when we divide those two, we would get the molarity of the solution to be 8.36 times 10 to the negative second molarity. Keeping in mind that that concentration right there can change if the room warms up. It's going to change the density of the water that it's dissolved in, which is going to make it actually get a little bit bigger, and so the concentration therefore would go down because the volume would get larger. Here's an example with mole fraction. So we want to find the mole fraction of potassium hydroxide in water in a solution that has been prepared by dissolving 1.5 moles of potassium hydroxide in 1 kilogram of water. Okay, so we have 1,000 grams of water, and 1 mole of water weighs 18.02 grams, which means we have 56 moles worth of water. So that's our total moles of water, and we already have our moles of potassium hydroxide. So the mole fraction of potassium hydroxide, KOH, is going to be equal to the moles of KOH, which is 1.5 moles, divided by the total number of moles inside the solution. So we have 1.5 moles of potassium hydroxide, plus the 56 moles of water that we just found. And so then the mole fraction with respect to potassium hydroxide is going to be 0.026, and there's no units on this because it's a fraction. Now, we could find the fraction of water by doing the same process, but I'm not going to. I'm going to show you a different way just so we kind of understand what this is showing. So a fraction is basically kind of like a percent with the decimal place moved over. And so if we think of percents, this would be 100% of a solution. So it would be a certain percent of potassium hydroxide, certain percent of water, and those two percentages would add together to be 100. Hopefully you recognize that. So then the mole fractions of potassium hydroxide plus water should add together to be what? Well, they should be 1. And so the mole fraction of potassium hydroxide plus the fraction of water should, in theory, equal out to be 1. If it doesn't add up to be 1, that means we did something wrong. Because if we've got a certain system, it's impossible for it to be more or less than 100%. And so then if we subtract 0.026 from 1 from our total, we would get our mole fraction of water, and we find that it's 0.974.